This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
This is Software Engineering Radio, the podcast for professional developers. Our guest today is Leslie Lamport. His accomplishments include a recent Turing Award for his work in distributed systems, as well as the document writing and formatting tool LaTex. Recently, Leslie has been focusing on TLA, which stands for Temporal Logic of Actions. TLA Plus is a specification language that is well suited for writing high-level specifications of concurrent and distributed systems. Leslie Lamport, thanks for coming on Software Engineering Radio.
My pleasure.
So congrats on your recent Turing Award. It's for your work in the area of distributed and concurrent systems. How do you define a distributed system?
Well, it's not something I've thought about recently. The definition I used to have is it's a multi-process system in which the time required for inter-process communication is large compared to the time taken for the time between events in a single processor. In other words, where it takes a processor a lot longer to exchange messages with another processor than it does for it to access its own memory. But as I said, that was a definition that I made up about 30 or 40 years ago. Nowadays, distributed systems seem to have evolved to mean systems in which processors communicate by sending messages.
Does that change sort of your formalized definition of it, or do you think of that as more of like a newer applied definition?
The formalism doesn't really depend on the definition of distributed, though that depends what you mean by formalism. Do you mean what I'm talking about by formalism here is how you go about specifying and reasoning about a distributed system, which is no different from how you go about reasoning or specifying any other concurrent system.
Sure, yeah, that makes sense. And when did you start thinking about distributed systems? I know you said it was a while ago, but sort of what led you to thinking about them?
I'm not sure when I started thinking about them. I think it was when I received a technical report by Johnson and Thomas, the one that's cited in my Time Clocks paper. I don't remember offhand the title of that technical report, but I think it had something to do about distributed databases. At any rate, I got that technical report, and that's the first paper or thought I have ever had about distributed systems, as near as I can remember.
Do you remember it like piquing your interest in a certain way that was different than other subjects that you had studied prior?
Not different, I would say. I guess it the paper itself, which led directly to the Time Clocks paper, occurred because I observed that there was something not quite right in the way they had done things. In particular, that the algorithm they used had the effect of allowing a violation of causality. That is, where two events that will event A causally influence event B, yet in their algorithm, event B could be processed before event A. And the whole idea of the problem of that notion of causality came about because of my familiarity with special relativity. And I could it was totally obvious to me, looking at what was going on, that it was completely analogous to the situation in special relativity, where instead of, as in special relativity, causality had to do with whether or not one event could causally affect another, depended on whether or not information from one could physically reach the other because of the finite speed of transmission of light. Or to try to put it a little bit more coherently, in special relativity, one event preceded another if it was possible to transmit information from the first event to the second event using beams of light. And it was clear to me that the corresponding concept in a distributed system is one event preceded another event if it was possible for information to flow from event A to event B by messages sent through the system.
Okay, yeah. So that did that lead to, I guess, your development of vector clocks, and then from then on, just your further developments in distributed systems?
Well, it led to what I called logical clocks, and some people now call Lamport clocks, which are somewhat different from vector clocks, which was a development. I don't remember by whom, but it happened not long after my time clocks paper. It had the effect on that paper was twofold. First, it got me thinking about the notion of causality in distributed systems, which is what the paper that time clocks paper was noted for. It also led me to realize that the algorithm that I came up with, which was a modification of the algorithm by Johnson and Thomas, applied not just to the problem they were looking at, which was, as I recall, distributed databases, but applied to any system. I realized that, and here I'm not sure exactly what led to that realization, but the realization that any system can be described as a state machine, and using the algorithm that is my adaptation of the Johnson-Thomas algorithm, one could implement an arbitrary state machine in a distributed system.
Right. Okay. So when I took distributed systems in college, I felt like the course material was divided into two sections. The first section was sort of material that we learned before we studied Paxos, and I felt like it sort of worked up to Paxos. And then the rest of the material was related to Paxos, and included Paxos itself. And my professor stated over and over again the importance of the Paxos algorithm. Could you talk a bit about your Paxos algorithm and what it solves?
Well, it was actually the second major step past the time clocks paper. Namely, the time clocks paper implemented a state machine in a distributed system, assuming no failures. So the obvious question was, how do you do it with failures? And that was one of the next things I did after the time clocks paper. Now, in those days, computer networks didn't really exist, or they probably existed in the sense that their engineers had hooked computers together, but they certainly weren't very common. And it wasn't clear in what direction practical networks would go. And so I considered the problem more or less in the abstract. And I had an intuitive sense that in order to deal with failures, one needed to use real time. The reasoning that led me to that was just very naive. It was the idea that the only way that you can tell that a process had failed, rather than that it was just going very slowly, is that it didn't do something in time. And that without a notion of time, you really couldn't talk about the notion of failure. And so the first algorithm that I came up with was one that was based on time. That is, it assumed a synchronous communication network, meaning that when in the absence of failure, a message would be delivered within a fixed bounded length of time. And so if a message hadn't arrived when it was supposed to, you could deduce that a failure had occurred. And using that, I came up with an algorithm that extended the time clocks idea to deal with failures. And again, since the notion of even what constituted a failure was not well developed, or there was no standard idea of what kind of failure one should handle, I considered arbitrary failures, namely failures in which processes not only could just stop working, but could actually compute the wrong result.
Are these also known as Byzantine faults?
Yeah, these are the faults that are now known as Byzantine faults. So I came up with an algorithm that handled Byzantine faults. That was shortly before I went to SRI. And when I arrived at SRI, I learned that the people there were in fact working on Byzantine failures and working on the exact sort of network that I had posited. Namely, SRI had a contract to design a very reliable computer system for flying airplanes. It was a NASA contract. And being reliable meant it had to handle failures, which meant you had to have a network of separate computers, since any individual computer could fail. And they realized that something that hadn't been realized before, namely that the presence of Byzantine failures could really complicate matters. In particular, the obvious way of handling failures by majority voting, namely that you have, say, 3 processors and one of them makes a mistake, you can use voting on their outputs, and as long as 2 of them were correct, then you get the right result. And what they discovered was that didn't work in the presence of Byzantine failures, because if a process didn't just compute the wrong answer, but it gave different answers, or reported different answers to different processors, then that could really screw things up. And they proved that to handle one failed computer, you needed not 3 computers, but 4 computers. Well, it turned out that my algorithm actually handled one failure with 3 computers, but that's because I was making an assumption or using something that they weren't. Namely, my algorithm depended on digital signatures, something which at that time very few people had even heard about. But when I got there, basically what I had done was combined with what they had done and appeared as a paper.
Is this the part-time parliament that you're talking about?
No. This was the reaching agreement in the presence of faults. The paper was, the authors were Rob Shostak, Marshall Pease, and me. And that was the work that initiated Byzantine generals I realized that this was an important problem and that the results in that paper were important. And in order to get it more widely appreciated, I invented the idea of describing the problem in terms of Byzantine generals. And so we wrote another paper. It had some new results, the major result being a simpler way of presenting the algorithm without digital signatures in the original paper, but it introduced the terminology of Byzantine generals and Byzantine agreement, and I think that had a lot to do with the paper getting to be so well known and Byzantine agreement becoming such a popular problem.
Yeah, I wanted to talk a bit about the notion of I guess using allegory or metaphor in order to describe these complex problems. So, for example, your paper on Paxos was the part-time parliament, or well, one of your papers on Paxos, the part-time parliament, and it's this allegory about a Greek island and the legislative process that the people of the island use. And I guess I want to read like a small section from it, just so the listeners kind of get an idea of what the paper lays things out in terms of. So one section from it is, as Paxos prospered, legislators became very busy. Parliament could no longer handle all details of government, so a bureaucracy was established. Instead of passing a decree to declare whether each lot of cheese was fit for sale, Parliament passed a decree appointing a cheese inspector to make those decisions. So I just find it very interesting that this is like a sophisticated, like super important paper, and you chose to describe it in these kind of story-like terms. And I guess I'm curious how you chose to approach a problem in this manner, and if you thought it helped you explain the problem, or if you thought it would just help with communicating the problem to other people. Like, I'm just trying to get some insight into your process for that. Okay.
This happened, well, it all is due to Edgar Dijkstra. He has one problem that he introduced, which is called the dining philosopher's problem. And it's a problem that, to me, never seemed particularly interesting. I mean, Dijkstra was a brilliant computer scientist, and he did some marvelous things, and I think that the dining philosopher's problem were among the least interesting things he did. But it became very popular and still known and talked about today because it had a cute story. In that case, the story was one of a group of philosophers sitting around a table, and they were eating some complicated kind of spaghetti that required 2 forks, and there was 1 fork, and each fork was shared between 2 philosophers, and pretty silly, but catchy, and that caught people's attention. So I think that's behind my reason for introducing Byzantine generals. And I realized that a cute story could gain people's attention. And that worked great with Byzantine generals. So when I devised the Paxos algorithm, I decided to do it again and came up with the Greek island. Basically, that was a disaster. I think it delayed the appreciation of the algorithm by close to a decade. About the one thing that it did achieve is gave the algorithm a nice short name, Paxos. So that probably helped. But other than that, it was a disaster. I did make use of the story to present technical ideas. For example, the cheese inspector was my way of describing what is now known as leases, the idea of giving a resource to a processor, but giving it for a fixed amount of time so that in case the processor crashed or failed, you could then later give that resource to some other processor. So that's a somewhat important idea in how you use Paxos to build a real system. And I presented that idea in terms of the, the cheese czar or something. At any rate.
So did you think of any of these ideas as you were explaining things in these terms, or did you already have these ideas and you just turned them into the fictionalized?
No. The ideas had nothing to do with the story. The story was just a way of presenting the ideas.
Sure. I guess I'm just saying, like, once you were sort of in the mode of this storytelling, did you think of any, fictional roles and you were like, oh, maybe I should actually invent a practical reason for why this character would exist in this legislature?
No. It was completely the other way around.
Okay.
And it was a disaster because I don't think any readers, very few readers, understood that this cheese inspector was in fact a description of leases and how they would be used in a real system. Another trick I used, taking advantage of the story that this was an ancient civilization discovered through archaeological excavation, when there were implementation details that I thought were pretty straightforward and not worth taking the time to discuss, I would say something like the archaeological records did not indicate exactly how the parliament did this.
Right.
I don't know if anybody appreciated or understood what I was doing in that sense. As far as I know, the one person who actually understood the paper when he first read it was Butler Lampson, and he recognized its significance, and it was basically due to his writing and lecturing about it, telling people that they should use Paxos, that Paxos eventually got to be well known.
So when I was preparing for this interview, I watched a recent talk that you gave called Thinking for Programmers. And you emphasized the need to think before starting to write a program. And you said that in order to think, you have to write if you want to think effectively. And you give the example of an architect blueprinting a house to draw an analogy with how a programmer must similarly write a spec in order to elucidate the solution that he's trying to reach.
Yeah.
So was the part-time parliament, was that a spec for Paxos, or was that just like a sort of a more elaborate description of it that was maybe the opposite?
Well, the paper told the story to explain what was going on, what the algorithm was accomplishing, and a little bit about, to give a little idea of how it worked. But that paper also included a very rigorous specification of the algorithm, which is purely mathematical, and a correctness proof, that is a proof that it satisfied certain properties. So the story was there just to, in a misguided attempt, to help people understand the algorithm intuitively. But the actual algorithm, the actual specification of the algorithm, which was in the paper, was quite rigorous, and there was no story behind it. It was basically just mathematics.
Right. And could you talk a bit more about what you were trying to convey in your talk about thinking for programmers?
I've come to the conclusion that a lot of the problems that exist in software, a lot of the problems that one encounters in building a system, writing a program, those are problems that are caused by not thinking about what you are doing before starting to code. And I have a sense that if you're building a complicated system, the battle is won or lost before a single piece of code is written. That is, the success really depends on the conception of the problem, the design of the system, not in the details of how it's coded. Best way to give an example of that is, suppose you want to write a sorting program. Well, if the only sorting algorithm you know is bubble sort, by the way, will the listeners understand what bubble sort is, or should I give a simpler example?
They'll
okay.
Understand.
So, bubble sort is not a very efficient way of sorting. And if the only idea you have of how to sort is bubble sort, then it doesn't matter how good a coder you are, no matter how wonderful, beautiful your code, how perfect it is, how wonderful your programming language, you're not going to produce a very good sorting program because it's going to sort slowly. So the way to write a good sorting program is to use a better algorithm, something like quicksort or heap sort or something like that. And so the idea of whether you're going to write a good sorting program or not is decided upon not by how good your coding is, but by the basic algorithm you're using. And that algorithm is chosen, or it should be chosen, before you start coding. You don't want to try to design a new sorting algorithm in C, because that's not the right level to be thinking of sorting algorithms. Well, there are many dimensions in which fundamental algorithms or fundamental designs can differ. One of them is computational complexity, which is now a fairly obvious one. And so if somebody has a well-defined algorithm a well-defined problem that's been well studied, such as sorting or maybe computing various things on graphs, well, he knows to go to an algorithms book and look up how you solve that problem and find the right algorithm before starting to code. But there are lots of things that we have to do for which nobody has designed an algorithm. And so for those things, you need to stop and think. And that thinking needs to be done before you start coding. And the thinking is really independent of the coding process. The difference between, if you're thinking about bubble sort versus quicksort, everything you're thinking about applies no matter what language you're coding in. Well, in addition to computational complexity, there are other important aspects of a design or an algorithm, in particular simplicity. And just like you're not going to find the best algorithm in terms of computational complexity by coding, similarly, you're not going to come up with a simple design through any kind of coding techniques, through any kind of programming language concepts. This kind of simplicity has to be achieved above the code level before you get to the point which you worry about how you actually implement this thing in code. Now, when you're writing a program or building a system, there are basically two problems that have to be solved. One is, what should it do? And the second one is, how should it do it? Now, in principle, these are completely separate ideas. The one idea for sorting is, what does it mean to sort? Well, you take a particular list and you rearrange its elements so that they're in increasing order. That's the what. That has nothing to do with the how. The how is, are you using quicksort or bubble sort or heap sort? Now, those two concepts are not completely independent in the sense that you may, in principle, you could decide that you want to do something, the what, and then when it comes to programming it, you discover that, you can't. That is, you don't know how, or the how is too expensive, or something like that. So I don't mean to imply that what you should first do is think completely abstractly about, what something is supposed to do, and then, only then do you think about how you do it. I mean, part of engineering is understanding what you can do in practice and what you can't. But given that caveat, you really should understand what the system is doing before you try to implement it. So there are two separate things you want to specify about a program or a system: what it does and how it should do it. Sometimes it's obvious, it's what something is supposed to do. Like you say, you want to sort a list. Well, that's very straightforward. It doesn't require a very complicated specification to describe it. Other times, the really hard part of something is to decide what it's supposed to do. And it's really important to understand what something is supposed to do before you start to do it. And very often, once you've decided precisely what something is supposed to do, implementing it, the coding, the how, is quite trivial. And it hardly needs a specification at all, or it might be so simple that you really can just start coding without writing any precise description of how it does it. Beyond the specification of what it's supposed to do, or in other words, how it's supposed to do it, is so obvious given what it's supposed to do that you may not need a specification of how.
And so the composition of this spec, should this be done in maybe like iterative drafts as you're thinking about the problem? Because you say that, in order to be actually thinking about a problem, you need to be writing. So is there like some sort of stream of consciousness process that you go through before you sit down and say, okay, now I'm going into spec writing mode? Or do you just sort of write a spec and then iterate on it and then move on to the program writing phase?
Well, first of all, there are lots of different things that can go by the name of specification. And I use all of them. Sometimes the specification I write is a few English sentences. Sometimes it's a very complicated mathematical description of the object, either the what or the how. It depends, which one is appropriate depends on the problem, how hard the problem is, how important it is that it get done correctly, and various things like that. And it's not like, anything you do is an iterative process. You start by thinking about something, and then you start writing it. And in the course of writing, you rewrite, and you rewrite, and you rewrite. Now, a specification can be anything from a few English sentences to a completely formal mathematical description of what or how the program is supposed to do things. I use all of them. Depends on how difficult the problem is and how important it is that the program be correct. A lot of programs I write just for my own use, and I can live with bugs, and it's not that important that they be absolutely correct. But sometimes I write code for other people to use, and I really want it to work right.
So at the end of the talk that you gave, someone asked a question about using UML to describe systems. And from the response that you gave, I kind of got the impression that maybe you had some disdain for describing distributed systems in terms of boxes and arrows. and you suggested the use of predicates and next state relationships. And I'm curious whether the notation is really the issue, because it seems to me that boxes and arrows are essentially the same thing as predicates and next state relationships. So is it just the usage of those two things?
No, the important thing is not, what you're, the syntax of what you're writing. The important thing is the precision, the rigor, that in order to understand things, you have to write them precisely. And I use mathematics because that is precise. UML, what I know next to nothing about UML, but what I do know is the language was invented first, and then people came around and tried to give semantics to the language. Well, in other words, what that means is that the language was invented first, and it really didn't mean anything. And then later on, people came around to try to figure out what it meant. Well, that's not the way to design a specification language. The importance of a specification language is to specify something precisely. And therefore, what you write, the specification you write, has to have a precise, rigorous meaning.
So for people that don't have the the mathematical chops to be able to write according to the formalities of the predicate and next state relationship syntax, is UML sort of an excusable next option? Because if it's between learning predicate next state relationship syntax and if the other option is making a more sloppy spec, but then trying to write code and then hack it out from there.
Okay, your whole question is based on false premise.
Okay.
You're basically saying, well, if people can't think precisely, should they just draw fuzzy pictures of boxes and arrows?
Right.
Well, people who are programmers should be able to think precisely, because you have to be able to think precisely to write code. And when you say they don't have the mathematical chops, that's nonsense. The mathematics that one needs in order to write specifications is a lot simpler than any programming language. It's really, the mathematics you need is what you learn in an undergraduate course on discrete math. Basically, first order logic, sets and functions. What has to be learned is how you use that to specify software. And that takes some education, that takes some learning. I have a mathematical language for doing that. It's called TLA+. Your listeners can find it on the web. You just go to my homepage, and there's a link, I think it's called, to the TLA webpage or something like that. And they'll find there's a hypertext book, which is the best way to start learning it. But as someone said, this is not rocket surgery. This is really simple. Unfortunately, mathematical education, at least in this country, is such that it tends to make people frightened of math. But anyone who can write C code, should have no trouble understanding simple math, because C code is a hell of a lot more complicated than simple math. And again, the important thing is not so much the language. I mean, I use math. There are other specification languages that are fine. The important thing is thinking precisely. the benefit of using math is that it teaches you to think rigorously, to think precisely. And the important point is the precise thinking. And so what you need to avoid at all costs is any language that's all syntax and no semantics, because that is not going to get you to think rigorously. That's going to get you to fool yourself into thinking that you're thinking.
To start to cap things off, how has your thinking about distributed systems changed since you started working on the subject? And I guess since distributed systems have become more and more necessary for the average programmer to understand and work with?
Well, I'm not sure exactly what you mean by how has my thinking changed. I mean, my basic mode of thinking hasn't changed. It's basically the idea that I want to understand things, and understand things for me means being able to describe them mathematically.
I guess what I mean is, has the landscape changed such that new situations and problems have developed that have exposed you to things that you hadn't tackled before?
Oh, the world has changed enormously, and new problems come up that are interesting. There's been an enormous amount of theoretical work that is in algorithms and theory that's been done on distributed systems. Unfortunately, I can't really give you a very good answer on that because I do very little work on distributed systems these days. I haven't for about a dozen years. I dabble a little bit, mostly because I have friends and colleagues who are interested and they will get me thinking about something. But most of my work has been on specification and verification.
Do you see yourself moving back into that field at all in the future and maybe working on them again?
I think it's unlikely. I'm now 73 years old, and I don't have that much of my career ahead of me. So, at least for now, I'm thinking of really continuing and trying to in some sense, finish up what I've been doing on specification.
Sure. And so I guess I have one more question. So I'm kind of curious about this in the realm of thinking for programmers. This wasn't exactly in the scope of your discussion, but I feel like it's important for thinking for programmers. How do you build the mental resolve to work through a problem? I mean, maybe this isn't something you've had an issue with, but is there some sort of like courage or persistence or emotional characteristic that defines a programmer who is able to systematically break down a problem?
Well, I think I've had it easy, much easier than programmers have it, because I've been in an environment where I don't have hard deadlines, where I'm given the freedom to explore problems that I think are interesting and important. Programmers are in a much more difficult situation. They have a specific task to perform, and they have to get it done in a reasonable amount of time. Now, what I'm advocating for programmers is what I do myself. Everything I say about writing specification, you could look at code I've written, and you'll see that in most of the code, there are more comments, documentation, and specification of the code than there is code itself. And I do it because that produces a better program in less time. But it does that for me because I've been doing it for a long time, and I know how. Now, a programmer who has never done this before, never tried writing specifications before, it's really hard for him or her to sit down and do it in the context of his or her current job. It takes I'm not saying willpower isn't the word, it's incentive to learn how to write specifications. And it's essentially, it have to be done most programmers in their spare time before they get to the point where they can actually apply it and use it in practice. There's an article that has been written by a group of people at Amazon, and I believe will appear one of these months in Communications of the ACM, although I believe that it has the final acceptance has not been given yet, but I expect that it will appear. And that paper describes how TLA Plus, my specification language, came to be used in a group or among several groups at Amazon. And I think that will give an idea of what it takes for this new idea of specification to take hold. It requires someone with persistence and foresight to believe that this can be a solution to their problems. And it takes engineers and their managers who are willing to invest the time and effort to use it because they believe that it will give better results. And in the Amazon case, that has paid off for them. But when a programmer doesn't have something like that to point to as something that works in his own problem domain, in his own context, then it takes courage for a programmer to start doing that and to give it a try and to really try to make use of it and to really try to do things better than he or she is now doing them. And that takes courage for an ordinary programmer. It didn't take courage for me.
Okay, that's a great response. I really appreciate it. Okay, well, Leslie Lamport, thank you for coming on to Software Engineering Radio and giving an excellent and informative interview.
Well, thank you.
Leslie can be reached through his website, lamport.org. In the show notes, you can find links to some of his papers, as well as the talk I referred to in this episode, Thinking for Programmers. Thanks for listening to Software Engineering Radio. We want to know what you think. Go to iTunes and write a review of the show, stating your opinions. It would help us improve the show. Thanks.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or /dot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.